In this lecture, we will be learning about the concept of linear approximation. So first, let's think about a function, y equals f of x. Consider the point A on the x-axis fixed. So we'll draw a picture to go along with what we're discussing here. So here we have A. And the idea is we are starting off at A, and then we're going to move from A to A plus delta x. So we're shifting over by this step of size delta x. So that's this width here. Now we have some function. So this is our function f of x. And the idea is initially we are here at the point A, f of a. And then after the move, we're at the point A plus delta x, f of a plus delta x. And the issue we will address is by making this step to the right in this picture of size delta x from A, what's the resulting change in y? And the resulting change in y is the difference between the y values, which we will call delta y. And in particular, that's what we are calling the increment. So the change in y resulting from the change in A of delta x is the increment, delta y. And again, you see that the length of this interval here is nothing more than f of a plus delta x minus f of a, this expression here. So this gives us, if you make this change in x, this is the resulting change in y. Now, what we're going to try doing instead is, what if we move along the tangent line? So we can redraw our picture here. So let's see if we can get something that looks similar to what we drew there. We had A and A plus delta x. And our function was looking something like this. So here we had f of a. Here is f of a plus delta x. And so this was our delta y. This was our delta x. Now the idea of the linear approximation is based on something that we know quite a bit about from studying differential calculus, and it's nothing more than using the tangent line. So instead of, as a shifts over to a plus delta x, instead of cruising along the function itself, what if we form the tangent line at x equals a, and instead of moving along the curve, we move along the tangent line. So we move to the point here. This difference is what we call dy. And that is what we define as this differential. So we're moving, again, instead of moving along the function, we move along the tangent line. And where we're going with this is that you can use the y value at this point to approximate the y value at this point. Now, it looks like a bad approximation, but things are kind of scaled up so that we can see the difference. You want to imagine this action going on down in here. We just wouldn't be able to draw a very good picture. Or if we actually zoomed in, we would see the same kind of thing as what we see now if it was happening here. So the idea is if delta x is small, using this dy to approximate delta y can work. And that's how we get the linear approximation. So this was our dy, and here we had our delta y. And so the idea is we use dy to approximate delta y. And again, delta y is the actual change in y as a result of moving from a to a plus delta x. dy is the resulting change where instead if we looked at the function itself, we moved along the tangent line. So if we use dy to approximate delta y, this version of dy here that is nothing more than this left-hand side. That should be delta x. And then, of course, this side on the increment is the right-hand side of this equation 3. So this equation 3 is simply taking this idea, using that differential, using that linear move in y to approximate the actual move in y. And to get the definition of the linear approximation, we solve for this term here. So notice that what we're calling L sub a of x is nothing more than this expression solving for f of a plus delta x. So that f of a plus delta x above equals this linear approximation. All this is saying is take that idea that we had. So let's draw a simpler picture. Here's x equals a. Here's our f of x. This is the point a, f of a. What this is, all this is saying, this is just a fancy word or a fancy equation for the tangent line at x equals a. So the tangent line at x equals a is exactly this y equals L sub a of x. And the argument is that near a, so for x near a, L sub a of x is often a good approximation for f of x. So looking at the picture, you can kind of imagine here, if you're really close to a, this lavender line is very close to the black curve of y equals f of x. And that's all the linear approximation it is. It's just saying form the tangent line and use the tangent line instead of the function nearby. Now, why might you do this? When you first see calculus, you may wonder why you worry about doing approximations. Usually you're given a function that's nice that you can deal with, you can graph. In many real applications, functions are not like that. And you may not even know what they are, but you may be able to approximate them. You can approximate them linearly, and that's often good enough if you can say something about the error for the situation that you're working in. And so this is used in mathematics, science, and engineering on a massive scale. Let's see this in action in an example. So suppose that we have this function, root 1 plus x, and we want to find the linear approximation at a equals 0. So first of all, we can just go ahead and quote, remember, our linear approximation, in this case near 0, a is 0, will be f of 0 plus f prime of 0 times the quantity x minus 0. So we just need to figure out f of 0 and f prime of 0. F of 0, we simply plug in x equals 0. We get root 1 or 1. Looks like we'll need our derivative. So f prime of x, we should rewrite our f of x so that we can differentiate it more easily, rewriting the square root as a 1/2 power. So we use power rule on the outer function, 1/2 times the inner function left alone to the minus 1/2 times the derivative of the inner function, which is just 1. So this is 1 over 2 times the square root of 1 plus x. Now note, we need this evaluated at 0. So f prime of 0 is 1 over, you say we get 2 times root 1, or 2. Plugging these in to our linear approximation, we get that L0 of x is f of 0, which was 1, plus f prime of 0, which is a half, times x minus 0. So 1 plus 1/2 x. Let's look at the graph and see what we just did. So first let's graph the function itself. And note the function itself, you have y equals root 1 plus x. If you square both sides, this is y squared equals 1 plus x, or x equals y squared minus 1. It's just the top half of that, but this is the parabola that looks like this. So this is our function, y equals root 1 plus x. And what we just did was, in this linear approximation, we went up to this point. This was the point, 0, 1. F of 0 is 1. That's this point here. We found the slope at that point, which is a half. And then we drew the tangent line, which is this linear approximation. And the idea is that for x values near 0, this is a pretty good approximation. But again, when you see this concept of linear approximation, it's nothing more than the tangent line generated at the point. But let's write this formally. So for x near 0, root 1 plus x is pretty close to this line 1 plus 1/2 x, which was our linear approximation. Sometimes you'll find yourself asked questions that are not necessarily specifying that you should use the linear approximation. And this next example is a case like that. We're just asked to approximate the 4th root of 15. So let's think about this. Fourth root of 15 that's 15 to the 1/4 power. And let's think, are there any numbers near 15 where this works out nicely? And we note that 16, which is nearby, the fourth root of 16 is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is a nice function that we could deal with. Well, let me back up. The function will be the fourth root of x, and this function is nice at 16. So f is easy to evaluate at x equals 16. So let's set a equals 16 and find that linear approximation. Then use that this L16 of 15 can be used to approximate f of 15. F of 15, of course, being the fourth root of 15. So this linear approximation, we use the information at a equals 16 because the function is nice there, easy to deal with. And then we look one unit nearby when x is 15. But instead of looking at the function itself, we look at the linear approximation. So our linear approximation, in our notation, what we would call L16, would be f of 16 plus f prime of 16 times quantity x minus 16. Again, this is just using the definition of linear approximation. So first, we know, we've already argued that f of 16 is 2. The fourth root of 16 is 2. We'll need f prime. So x to the 1/4, when we differentiate that, power rule, 1/4 x to the 1/4 minus 4/4, or the negative 3/4. We now need to evaluate this at our a, which is 16. So f prime of 16 is 1/4, 16 to the minus 3/4. Let's rewrite this. Let's put that 16 in the denominator. So we get 1/4 times 16 to the 3/4. And then we can rewrite that 16 to the 3/4 as 16 to the 1/4 cubed. 16 to the 1/4 is 2. And so this is 1/4 times 8, or 1/32. And that's what we're putting here. So our linear approximation is, as we set up here, 2 plus 1/32 times quantity x minus 16. But remember, we want to check this linear approximation. We were calling it L16. L16 at x equals 15. So this is 2 plus 1/32 times 15 minus 16. Again, we're just plugging 15 in for x. And when we do that, we get 2 minus 1/32, or 64 minus 1/32, or 63 over 32, which is just a little bit less than 2. That's actually 1.96875. Now the answer to a higher level of accuracy, so a closer answer, is 15 to the 1/4 is approximately 1.9679897. And you'll notice here we match actually to the first 3 digits if you were to round this up. So we did a pretty good job of approximating this. Our approximation was quite close. And it's worth noting, I think there's a tendency to look at a question like this and say, why would we do this when we can just plug 15 to the 1/4 into a machine, to a calculator, and get this answer? Well, the issue is, what is the calculator doing? 15 to the 1/4 is an irrational number, non-repeating, never-ending decimal. Your calculator is also approximating it. It's using a higher level version of what we just did here, but in essence, it's the same. It's the same principle, that this is in fact also an approximation just to higher level of accuracy. But your calculator is doing something very similar to what we're doing here. And if we wanted to look at the picture of what we just did, the function x to the 1/4 is something like this, and we built the linear approximation, aka the tangent line, here at this value, or at this point, which was the point 16.2, and then we went and evaluated that right nearby at 15. And the tangent line and the curve are very close to each other at x equals 15. In fact, we see just how close they are here to the 3rd decimal point. So this is a very common use of tangent lines, this idea of linear approximation. If you continue with your calculus studies, you will learn more about this, a more sophisticated version of doing this, where you learn something called Taylor series and Taylor polynomials. And in that case, you can do you can think of it like doing a tangent line or a tangent parabola or a tangent cubic, where you can get closer and closer approximations. Now, that being said, an approximation is only any good if you can say something about the error. We won't talk about the error approximations here. This is something that you'll learn, again, when you study Taylor series. But we at least want to define what we mean by error. And so we have 2 versions of error that we look at. One is the absolute error, which is kind of the natural thing to think of. It's just, what's the real value, the true value, minus the approximate value. So take the true value, subtract the approximate value, that's your error. The relative error converts things to percentage terms. So you take the ratio of the true value versus how much your error measurement is off by. So for instance, if I told you I was taking a measurement and my error was 1 foot, well, that error is going to be, you're going to interpret that very differently if we're interpreting that 1 foot as the error of, say, the width of the room you're sitting in, versus the error when we're measuring the distance from you to the closest point on the surface of the moon. And so this is why relative error is a key type of error to think about, because it really matters how far off you are on a percentage basis. So the relative error in the case, if we say the error of our measurement is a foot, if it's relative to the size of the width of the room you're sitting in, that'll be a pretty big percentage error when we compare it to the relative error of your distance, the distance from you to the closest point to you on the moon. It'll be a much smaller relative error there because the denominator will be so much bigger. In the example that we just did, our absolute error, so remember we were using f of x was x to the 1/4, and then we had what we were calling L16 of x. This was the linear approximation. So the actual answer minus the approximated answer, the absolute error was negative 0.00076. And on a percentage basis, the relative error was about 0.04%, which is pretty small. And so it's always good to be conscious of your error anytime you're doing an approximation. And then again, when you get into the topic of series, Taylor series, and one of the most important theorems in calculus, Taylor's theorem, give us a way to handle the error, to estimate the error for these types of approximations. The last thing we want to do is take one more step with this idea of the differential and recognize this was the equation that we had used for our linear approximation. And it came from writing this as f of x plus delta x minus f of x was approximately f prime of x times delta x. This was our increment delta y. Now the idea is shrink delta x. Think about making it infinitesimally small. And then we replace that delta x on the right with dx. And the delta y with dy. So this delta y will become dy, and this delta x becomes dx. So think in a limiting sense, shrinking these down to something infinitesimal. And the result is that we have dy equals f prime of x dx. And this is where we see our differential notation from before. Think of dividing both sides by this very small quantity dx. And so this is how we define the differential. And this will be particularly handy when you start doing integral calculus. But for instance here, we have some examples. We know that the derivative of cosine of x is minus sine of x, and we have our dx. So we're using that definition on the previous page, that dy was equal to f prime of x dx. And when we're asked to calculate a differential, this is what we use, and you can see this is exactly what we're doing. So think of dividing both sides by dx. Here, this differential, we use our differentiation rules. The derivative of e to the minus 2t with respect to t would be e to the minus 2t. That's the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function, which is minus 2. And then we have our dt. And if we wanted something like the derivative of u times v, this would be our product rule. First times the differential of the second plus the second times the differential of the first. And again, this is something that you will use much more when you study integral calculus. So you'll see this again. But really, to wrap up this idea that we've looked at here of linear approximation, calculus textbooks often present it in a way that's excessively complicated. Really, all it is saying if your function is differentiable and you're at a point and you want to approximate the function near that point, just form the tangent line and use the tangent line for x near the point at which you generated the tangent line. And again, this is a very standard thing in math, science, and engineering. It's used profusely. So this is something that's good to become comfortable with and to learn well.